Hello and welcome everyone. Today we are here to build a project that will be estimating the house price of the Boston dataset, for which we are using the Anaconda Navigator, under which we are using the Jupyter Notebook, and the Jupyter Notebook provides us with the cells under which we can write and execute our code in a very efficient way. I have taken a new notebook. You can do the same by choosing the file, new, and here you get the option of notebook. And I have named my notebook as linear regression because I'll be using the linear regression module to present the project output. I have given a heading of data pre-processing, that is, we are going to load the data. Before loading the data, we'll be importing some important libraries which are helpful in using the many functions Python has inbuilt in it. For this, here we have imported some of the important libraries that we'll be using very efficiently in our code ahead. That is the NumPy, which is abbreviated as NP. This NumPy library is used to do the vectorized operation. Next, we have imported the pandas as PD. This is used to study and notice the details about the data sets and the data structures that we'll be using. Next comes up the matplotlib, and that we have imported as MPL. The matplotlib is used to draw the graphs and see the image of the functions and the properties that we are using. Next comes up the matplotlibs.pyplot. This function is again used to draw the graphs and visualize the estimates of the data. Next comes up matplotlib.animation, from which we are importing the func animation operation of the library. This animation, the data changes, we can visualize as it forms. The matplotlib.animation helps us form the movable graphs. It gives us an animated image of the graph, which helps us to understand the graph in a more efficient way. Next is the sklearn. This library is the most efficient library of the Python, which helps us import various other libraries and make the use of it. The sklearn, which stands for the scikit-learn. This has a data set of load underscore Boston. So we are using the same data. And then is the matrices, which is importing the mean squared error. It helps us to find the mean square value between the predicted values and the original values. The next is a model selection, from which we are importing the train, test, and split. As in many of the machine learning modules, we are using the data in two fractions, that is in the training section and the test section. We can divide it as per our requirement. So in this model, I will be using 80% data as the training data and 20% data as the testing data. And for this, the train, test, split model is used. Next, we have this sklearn pre-processing min-max scalar. This min-max scalar library helps us to understand what is the maximum and the minimum value of the data set. That means the range in which our data set is lying. The last but not the least is the ipython.display, from which we are importing the various features of HTML and we will be using them. If you're worried about what is this NPPD, why we are importing NumPy as NP and pandas as PD, we are using these abbreviations as it makes our working go ahead very faster and most effectively. Now here we have mentioned the steps under which we'll be involving. The first is the data pre-processing, in which we will be accessing the data and getting it into our module. Then we will be defining the error. This defines the percentage of errors that we are having or going to have in the project. Next, after defining the error precisely, we will be doing the splitting of the data into two parts, that is the training data and the testing data, which we'll be knowing more about as we go ahead. Then comes a training the model. We'll be training a model. We'll be using the linear regression model to do the training, and at last the model, according to the training that we have given, will be giving us the prediction of the Boston house price. The first step is the data pre-processing. Here we are loading the data. Here I am loading the Boston data under a variable called Boston. From the load underscore Boston. We are also going to get the description of the data as this data set is already provided by the sklearn, so the description of the data is also in it. So we'll be just extracting it. Dot DSCR. Here we have loaded the description. It gives us all the features that we'll be using, the CRIM, Zen, then Indus, Chaos, and lot many more that we'll be using. These are the key features that help us understand what the data is all about. Here we go. Now we are going to import all the features of the data under a variable called features. We'll be doing this by using the pandas. Basically, we are loading our data frame into a new data frame using the pandas. We are extracting all the features and the data available in the data set. This helps us visualize the data into a more effective form. Feature underscore names, and to see it we can execute it by writing features and execute it. As you can see here, we can see all the data in a nice tabular format which has got a basic indexing. We have a 506 rows of 13 columns. Here every description that was given, these description that we extracted is given on the top. This is showing the features. If we want to view any particular feature of the data set, then it is also possible by just a single line of code. As you can see, I took the age variable and all the age parameter data from 505 with its length and data type of float has been displayed along with a indexing. Now we are going to put the data set again into a new variable called target. We are using this data set to have an even clearer picture of the data. We'll be doing the same as we did, but we are extracting the different features. This time we are focusing on the target features, and we will be extracting the target. To see the target data, it's pretty simple. As we can see, we have got all the data of the target in the same tabular form as we got the above features in the variable feature. Here, this is all the data that we are going to use to make the estimation of all the things and the predictions. Now we have the target variable, so we can see the maximum target by using the target.max. This is also showing us the data type, that is float, or you can do this as I'll comment this. We can also get the maximum by using this function target and within the parentheses target. Here we get both are good. Similarly, we can find the minimum. I find this more comfortable as it gives me the data type as well. We are done with the minimum and the maximum target value. This means that our data will be ranging between 50.0 to 5.0. This means the data will be ranging from 5.0 to 50. We are going to concatenate the data of of the features and the target, we are using a variable called df to store it, and we'll be using again the pandas to concatenate. By default, the Python has a habit of concatenating the data one after the other, but we are using the access equals to 1, which helps us to concatenate the data one after the other. And to execute it, we'll just write df and shift alter. As you can see here, all the features of the data features has been printed, and at the last we have concatenated the target, which is printing the data side by side. And this works pretty fine for all the data entries from 0 to 505. We are getting all the 506 entries. Now we are going to describe the key features of the data set. For this helps us to visualize all the key features that we will be looking forward for the prediction. We'll be using the df.describe function, and we'll round the variable, all variables value, to a decimal of 2 points. I will use the comment here using the round function to provide the decimals up to 2 place and execute it. Here we get the key features of every minute detail that will help us to execute and have a precision of all the data. Like we have 506 data entries, the count shows us. We have a mean of 22.53. Here we have the standard deviation of 9.20. The minimum value starts from 5.0 as we have seen earlier. The maximum value is 50.0, and the 25% data is coming under the target of 17.02, 50% respectively, and 75% respectively as well. This gives us the precision that at what different stages, what is the value of the data set that we are going to use. Now here we are going to find the correlation between the features, the key features that we have shown up to now. The correlation helps us to know what is the best fit between the two target features. Like here we are just focusing that all the features that we have extracted from the features data set, what feature among all of it is having a direct relation with the highest peak to the target. We will be taking that feature as our key value to do the predictions and to train our model. The correlation tells us how closely the values of one column in the dataset depends on the values of the other column of the same dataset. Here, the higher the correlation values, the higher is the estimation. We have different values at different types of correlations that shows different values. The higher the correlation, the higher is the prediction rate to the accuracy. We have different ways to show the correlation, but we will use the statistics method here to show the correlation. This helps us to find and visualize the best fit in a very ease of access manner. Then if we have, like I said, that there are various types of correlations. If there is a high correlation, we get the higher predictions to the accuracy level, and if there is a low correlation between the two key features, then the prediction rate will definitely be affected. If the correlation rate is positive, then as the value of the x variable will increase, similarly the value of the y variable will increase. So, and the vice versa is for the negative correlation. As the value of the positive x variable increases, the value of y will decrease, and vice versa stands true. Whichever attribute is having the highest correlation with the target variable is the attribute that we will be focusing here for making the predictions. The correlation here provides us with a special function called core. This is the function provided by the pandas. This function specifies which correlation function to use. Here we are using the Pearson function. I will give the comment to understand. I will take a variable called core, and by using the pandas I will define the relation here. We are using the Pearson function here. Here we are using the Pearson function, which is helping us to find the highest relation to the target variable, as target variable is the function where we are getting the final output of all the key features, including the minimum, maximum. Therefore, the features that the features dataset provides needs to have a highest relation with the target, and the Pearson function helps us find it. There are also other functions of the correlation that the pandas dataset provide, but we are using Pearson here. To know more, you can refer the pandas data documentary. Here we are more interested in the absolute value. To extract the absolute value, we will take another function and take the features as we have done earlier. Call the name of the features one by one to display them together. The target, for the attribute, just a second, for the attribute in the list of features. Making the pair of the lists of the correlation and the features. Correlation and the features. We will be taking a new variable L and store it in the form of list by using the zip function. The zip function takes the multiple values and returns the tuple of, just a second, and returns the list of tuples in which each value is a tuple of the nth value and each value in the list. This is the function that helps us to ease the access to access the tuple finishing. Otherwise, there are other many features which you can use to show the functioning. Now we will be sorting the data set in descending order. So that we get the key feature which is having the maximum relation with the target should be at the first peak, and this makes us easy to visualize which data will be picking up for the prediction ahead, in which our correlation function is the key value. Now write the code for the sorting. We are using here the lambda function. The lambda function is the anonymous function which has no name, and it is basically used to perform any function for once. This is an anonymous function. This can be used when we are bound to use a function but we are not in any condition to define it as whole. The reverse value here we have set as true because we want the distribution in the descending order, as here by default the reverse value is false. So we will set it to true. That will help us display the function in the descending. As now we have got all the values sorted in the descending order and our variables all aligned as the way we want, now we will unzip the two pairs in the list by using the zip function again. We will be storing them into the two different variables in the form of list by using the zip function. We are again using here the zip function, as it takes the different elements and unpacks them into an individual. Thus, we have obtained the individual values matching their every value with the values of the target table. Let's now plot the correlation in the form of bar graphs. Let's put this as a comment so that we could understand that here we are plotting the graph. We are plotting the graphs here as the bar graphs because bar graphs are much more easier to understand. The next is we will be using the functions of matplotlib ahead. We are plotting the bar graphs for the code. Relations, and here we go. np dot range will be taking the length of the labels and fixing the size of the figure by using the fixed size function. By this we will be giving the values, in this will be the size in which they will be displayed. Make sure to give the spacing in accordance to the variables so that they should not collaborate and form a mess. This will be the width between each bar graph, that is 0.5. Now we will be putting the labels of the x-axis and the y-axis. This is completely not mandatory, but it is a good habit to put the labels. This makes us understand and give a clear idea about what the graph is. So here we put the label. This helps us understand what the axis is representing with the target, and the y-axis xy label and name it as attributes. Now we'll be using the name of the tables that we'll be using. Plot.x, xsticks, that is index, and labels. Now, as we are using the Jupyter notebook, it is not mandatory to write plt.show, but if you are using any other software, then plt.show is mandatory in order to print the bar graph. This else-that function, which is having the highest priority with the target, is the function which is showing the lowest status. If the lowest status value of any society is high, then definitely it is going to affect the prices. The prices of the houses will go low. So this is the way that we analyze each feature in a deep method in machine learning, so that we could give the estimated budget and estimated price of the module. That is, here we are doing the, we now here are going to normalize the data. As from the above bar graph, we have concluded that the LSTAT and RM are the features which are having the highest correlation with the target variable. So now we will be taking the LSTAT and RM value, in which also LSTAT is having the highest feature. So that will be our first priority to do the normalization. Now we have got from the bar graph that the LSTAT is having the highest priority with the target variable. So now we will be normalizing the data, that is, we will be preparing the data for the linear regression. Here our X will contain the values of the LSTAT column, that is the variable we have estimated is having the highest correlation with the target. Similarly, the Y variable will contain the values of the target column. We perform the normalization on the X and Y values now. We are performing the normalization here as we need to find the common estimate of both the values. As there are different data sets, the different data sets are different parameters on which their values are plotted. So normalization basically brings them to a common scale without distorting their original values. This normalization also has a feature by which we can put the data set back into its original state. But getting the features into a common parameter and then figuring the differences and similarities in their behavior helps us to know the functioning and the stat in which the LSTAT is having the most priority with the target value. Let's print some values before applying. Sorry, I did a spell mistake. Yeah. Do now a small exercise to understand. Let's try to print some values before applying the normalization. We'll print some values of Y and see the range in which it lies. Sorry, we are having a capital Y here. We can see that it is showing some arbitrary random values, but here our range is between -1 to 1 in order to understand the data. So now we'll be using the min-max scalar to use the function. We will use the min-max scalar function to apply the normalization. Min-max scalar is the function that helps us to put the data within a certain range and compresses the data set into a particular range so that both the values, that is the x values and y values, lie in that certain range and show the properties. Here we are having the random values which is before normalization. Now we'll be applying normalization to our data set so that we could get the values in a specific range. Here we are taking the range from -1 to 1, as I said earlier. So I take a variable called I take a variable called x scalar, and I'll be using the min max function. The min max scalar. The min max scalar stores the parameter in which it has to display the values. It provides the inverse transform function as well, which helps us to return it to its original value so that we could compare the original value and the predicted value. Then we are going to do the transformation. Here the x variable, we will use the fit transform function dot fit transform function. This transform functions is basically used to to transform the function from an arbitrary range to a definite range. This fit transform function basically displays the function after doing the sorting into a vertical form, but we don't need it in a vertical form, rather in a horizontal form. So we'll be using a numpy function, that is x dot reshape it and set it from -1 to 1. This is not necessary that always we know that where is the range, so we can also do this, that we select it from the beginning and give it an instance of -1, and it will automatically get reshaped. Then similarly we'll be doing the same for the target variable, that is the y. So this is where we apply the normalization, and now we execute it, and let us check the values after applying normalization. We will again print the values of the target variable, that is the y. And execute it. And here we see that the value is ranging from -1 to 1. Rather, it is ranging from 0 to 1 because we are not having any negative values yet. So this is it. Now, as we have successfully processed our data and have got it into the format in which we can use it in our data, now we are running towards the step 2, that is defining the error. Here we'll be examining our data, processing the data again, and finding how good is our data with the target variable so that we can have an estimate that a prediction is going to be accurate up to what extent. Our main objective is to minimize the error function. The error function is basically calculated by finding the difference between the true value and the predicted value. The true value is the value that is provided by the dataset, and the predicted value is the value that we will be providing as the prediction on the basis of our calculation ahead. We are having the regression loss function here. That is why we are using the linear regression module. Thus, to estimate the error, we are using the mean square error. We choose this error as it makes it easier to calculate the gradients, and it is pretty much easier to execute the mean square error as it is the function in which we are calculating the difference between the squares of the true value and the predicted value, and then we divide it by the number of contents. By using the mean square error, now we will be calculating the mean square. We will be making the prediction values. For that, I will be defining a function where my mxc and t will be the parameters, where m and c are my weights. I will give it the size of x, and e will store the errors, and here I will be giving the formula for the mean square function, as the mean square function consists of the exponent. So we will return the error 1 by 2 into our weight. Here we will be splitting the data set into two forms, that is the training set and the testing set. As I mentioned earlier, that I will be using the 20% of data for testing and the remaining 80% of my data for training. So now we are going to write a code for it. We will define the variables as xtrain, xtest, ytrain, and ytest. And now I will be using the function of train test split and pass all the parameters. That we need, and by using the test size function we will define the data that we'll be using for our testing set. Now I'll execute it. As now we have completed the step 3, that is to split the data set. Now we have to move on to the actual part of our project, that is the linear regression module, which we have selected as a basic module to complete this project. I would like to have a basic introduction of linear regression module before we start. That is, the linear regression module comes under the supervised learning module of machine learning. It has its origin from statistics. This module is a method that helps us to understand the relationship between the input and the output variables. This method is having a basic formula, that is y is equals to mx plus c. This is the equation of line, which is going to be the base for us to execute the errors and our predictions ahead. This is a module which supports the linear variable as well as the multiple value linear regression. In the single variable we are having only a x and a y, and for a single variable, as we give it to the project as input, it will be giving us the output in a single variable. For the multiple variable, it will be taking different parameters of the data set and will be giving us the output according to it. This module has a drawback, that this module does not fit for the modules that have the data set in distinct variables. It works, that means it doesn't work for the modules that needs. The gradient descent in linear regression is what we are going to understand first in order to get through the linear regression module. The gradient descent function is the last function that uses both the update function and the error function I mentioned above to calculate the gradient for the module. What a gradient is? The gradient is the minimum value of prediction that we'll be using to make the estimation of the price. The gradient descent algorithm helps us to calculate the gradient by using the values from the update as well as the error function that we'll be defining. But for that, we need to understand what these functions basically do. The gradient descent algorithm works on following steps as is visible on the screen. It starts with making an initial assumption for the m and c. The m and c are the slope m and the intercept c from the equation of line. We start at taking an assumption of a random value. You can also start by taking the minimum value, but this is not always very accurate or possible to do so. Therefore, starting at a random value, we'll be applying these values to the update function. This update function will help us get the values of the slope m and the intercept c. These, along with these, we'll be getting the error values, the error thresholds, and this will help us to find the cost function, that is also called as the error function. This will help us to find the calculate the gradient at its current position. Now, this current position will help us determine at what direction our movement is going on according to the data set that we have. And now, after having this movement, we will get to know this gradient descent will help us know every time the error values and the assumption values are calculating, they are updating the values of the slope m and the intercept c. We will be getting a learning rate, and this learning rate will help us understand what is the process or what is the way in which our data is proceeding and what will be the pattern in which we'll be making the predictions. Everything that I mentioned might not be very clear to understand, but as we go ahead and keep on doing the process as I mentioned, you will be getting every step very clear. Coming back to the update function, we need to understand what this update function does. Basically, this function is used to update the weights such that the values get closer to its actual values. Its purpose is to calculate the gradient and current position of the intercept c to update the slope and the intercept c. Now it needs to calculate the current values of the slope m and intercept c, for which it includes the parameters, that is the slope m, initial values of the slope m, the intercept c, attribute values of x, and the target values t, and the learning rates. The learning rate controls how much the weights change along with time. This is executed using the NumPy vectorized operation. To make the update function, we need to define a function called update, and I'll be taking all the parameters that are necessary for me to do this. As we go down, this m, x, c and t and the learning rate, these are all the parameters that will help me calculate the gradient. We'll be calculating the gradient here for the m as well as the c, that is the slope and the intercept respectively, and we'll be multiplying them in the end with the learning rate. The learning rate, as I mentioned earlier, helps us to understand what is the rate of change of the slope and the intercept along with time. So let's do that. We'll be taking a basic sum. We are making the formulas as simple as possible. And these are the basic mathematical formulas that we are using here. Just a second. Let me see. Alright, just a second. This has to be like this. As we go down, similarly we'll be calculating the gradient c. Sorry, underscore c makes it more readable. And the same we do. M into c. Sorry, m into x plus c. What did I do here? Okay, it's a x, that is my attribute value, minus, I'm multiplying it by x again. We now update our slope values with the new value and multiplying it with the learning rate that helps us understand the change. Sorry, this is the c, the change into the values along with the time. the gradient underscore C into the learning rate. In the end, we'll be returning the updated values of the slope and the intercept with this function. Now moving ahead, calculate the final gradient of the line formula that we have used in the update function. We have passed a few parameters for this function, that is init m, init c. These are the initial values of the slope and the intercept, which we will be initializing at some random point, which I defined when I defined the gradient. Now these functions will help us calculate the new error. The x and t are similarly helping to calculate the errors, whereas the x is the numpy array of the values of the independent variables, and t is again a numpy array that is the value of the target variable. The iterations we'll be using are for letting us know the number of iterations we will require to calculate the error, and error threshold, as I've defined above, this is defining the minimum number of errors that are allowed. Moving ahead, we have initialized our m and c to the initial parameters that we have taken, that is init m and init c. Now we are creating an empty list of error values. This list is used to store the intermediate error values during the training. It will help us later to see how the error values changes during the training course. Moving ahead, we have created again an empty list called mc values. These values are again this list is again used to store the intermediate values of m and c. We will in the end visualize how the values of the m and c are changing as we move ahead. Again, now we are making a for loop. This for loop is moving to the range of iterations that we will require to calculate the error. This again we now have if the error value, that is E, is less than the error threshold, then we will just print the message that we are breaking out and we have calculated what our error is. Now we are calculate the error value that we have calculated. We will append it to the list of error values so that it will store every value of error and we can visualize it in the end. Again, the c and the m, that is the slope and the intercept, we are again getting that updated. We are using the update function that we have defined above here, and we are using it here, calling that function and getting all the parameters that we'll be using. The parameters next is after we are getting done with calculating all these above parameters, we will be returning from this function the values of the slope, the values of intercept, error values, and MC values. This value of the slope and intercept will be the final value of our slope and intercept at the particular point. Successfully defining the gradient descent function. Now we have to pass them the executing parameters that will help them give the output. So I'll be passing the parameters in the respective order as they are mentioned above. Make sure to write it in the exact order. Learning rate, I'll put it as 0.001. Keep the learning rate really low because it is completely depending upon the stack overflow. If the value is exceeding then 0.025, then it will show you stack overflow error. So keep the value of your learning rate really low. I am keeping my iterations limited to 250. I think that will be sufficient for me. Then comes your error threshold. As I told you, this is the minimum value for the acceptance of errors allowed. So I'm keeping my error threshold value also really low. Now I'll be calling all my parameters in the exact same order as they are defined above. Error values and the MC values, and we'll be passing these values to a gradient function. So I'll just copy this from here and use it here. There are small changes that we'll be making because we are using the data from the training set. So we will use the training set parameters, that is the X train and Y train. Now we'll execute it. After passing all the parameters that we need for our function, now it's time that we have to visualize everything that we have done so far. For this, now we'll be using the different functions of matplotlib to plot the graphs to see what is actually happening. For this, I'm going to take a new variable called mcvalues underscore nm. My spelling has gone wrong. Okay, nm, and this value will be storing my all the values of the array that I have defined earlier, that is MC values. This MC values is going to have the starting and end point. I am setting the end point as 250 because I have set the iterations to 250 here. Now I'll be doing a third thing that is called slicing. I am doing the slicing here to reduce the CPU execution time. If you don't do the slicing, this is going to be working fine as you will get a really smooth graph, but this will require a greater time to execute. Thus, to reduce the CPU execution time, we are making use of the slicing function. Alright, we move ahead. Now what we are going to do is we are going to use a function called plt.subplots. It provides us with two objects, that is the figure and the axis. Under the plt.subplots, this function returns us the two objects that will be defining what is going to be my starting and ending point of the regression line. So moving ahead, we are going to define again a new variable called line, and this line function will be plotted using the plt.plot. For this, again, I'm going to pass different parameters. These two empty lists are going to be my x and y coordinates. I'll be defining them ahead. For my coordinates, I'll be using a color called red orange, and another variable that needs to be plotted here is animated, and I'm setting it to true. This defines that I want an animated image of my graph. Now what is we are going to do is we are going to define these two empty lists. What is the value that is going to be inside them? For that, I will define a new function called define init. Sorry, need some braces here. Yeah. Now plt.scatter. I'm using this function because I need the scattered image of all the x and y test dataset. So these are the parameters. This will plot them in a scattered way, not in a line or in a clubbed form, so that I can just visualize them very fine. And I'm going to set the limit of the axis. This will help my graph to understand up to where it has to exist. So I'll use the function set.xlimit to set the limits of my x-axis. I'm using it as 0 to 1.0. Similarly, I'll be using set.ylimit and setting that as 0 to 1.0 again. So we have defined how long and how far my graph is going to exist, and I'm returning all of this to my ln. I will define a new function called define update frame. For this, I'll be having a parameter called frame. What this function is going to do is that it will update the value of my regression with every time a new data point enters. Like if a new x enters, this will update the value of y and plot it, and my regression line will change. So for this, I need to pass my values of m, I forgot the m, and c here. That will come from my new variable that is storing all the intermediate values of the MC values array, and I'm going to have it in the form of a frame, as my frame is going to be updated. Now what we are going to do is we have to define the x and y. what happened to this X? I think the indentation has gone much. Yeah, X and Y. So for this also we need to have a starting point. So I'm passing my X as 0.5 and always the Y value has to be calculated with the equation of line. So we will use the formula of M into X, that is my minus 0.5 plus the intercept C. Similarly, the ending point has to be defined, that is the X2 and Y2. That is going to be, I will take it as 1.0 and again the equation of line. Alright, now what I'm going to do is like I'll set my data, like up to what extent my regression line has to go. So the line will also be set by using the set underscore data function, and my data has to lie in between x1 comma x2 and y1 comma y2. Okay, we will return everything back to the line as we have defined our line here. Now if you want to understand how your line looks like or what is the type of your line, you can just use the print function to see what is the function of your line here so far. Now what I'm going to do is like I am now actually going to make use of the func animation library that we have imported from Matplotlib in the very beginning of our project, so that we can get the animated graph. So I'm using a new variable called nm, and I'll be using the function called func animation. The func animation function requires two functions to be defined, of which it will be plotting the graph for. So I'm using the first one as fig, as the first function is init, but it is defining everything for the fig, that is standing for my figure that will plot the scattered image. So fig comes into play at first place, and the next function will have the name update frame because we have our next functions as update frame. Now this works pretty fine. We can plot our graph so far so fine with this, but it's a good habit to make the function understand what actually are the parameters and ranges up to which I want my function to work for. So I'll just define the frames up to which I want it. So I need a range which has to be just exactly up to what the length of my MC values underscore nm has. Now what I'm going to do is my init function, from where it is going to take the value of the figure, is that I'll define it is from the init, and in the end I'll set the blit equals to true. It is just the initial function of the func animation which sets the easy execution of the func animation. So just set it as true. If you want to have a greater data knowledge about it, so just Google it. Now what we are going to do is, now everything has been plotted, but I need my regression line to tell me where it is actually lying. So I'll be plotting my line here by using the plt.plot, and it is going to have my x test, and again equation of line as its y parameter x underscore test plus c. Then comes the color. I'll be setting the color to red this time so that I can see how far it works. Now we are going to need an animated image to be shown. For that I have imported the HTML library, and now I'll be using it. So it all has to be capitalized, and I'm going to use a function called to underscore HTML5 underscore video. Alright, I think this has to come down. Alright, and let's execute it. Oh, I forgot the comma here. As now you can see, I'm just not showing the animated image because it's take a lot more execution time. Here we see the graph, this red line this is passing through the maximum values of my data points. This is the regression line. That means it is showing that my prediction ahead is gonna be so much precise about what the data points are passing through. So in the end, the data may vary because my line is having its range from certain minus points to the point of 1. So my regression line is passing through almost all the points, therefore we are getting a pretty good rate. Now what we are going to do is like we are going to see if this is working fine with the testing data set as well. So now I'll be visualizing, sorry I have not put the pen sign here, right, training data visualization. We are just simply going to plot our testing data here by using the same function plt.scatter that will just put all my data into a scattered form so that I can see it. In this I am also taking the white train as direct because we already have the values, and now I'm just using a different color this time. Let's say blue. Blue is doing good for me. Then comes the plt.plot. We are going to plot these values and see how far this works so great. Now comes the train, and here when we are just, this scatter is taking the data points from the value that we already have, but the plotting data will calculate the values of my slope. So again we need to just put the equation of line here, m into x train, x train plus c, and I think this will also need a color. So my color is red again. For the line we'll use the red color because it shows pretty dark in there. See, this is working really fine here. Like from the point where I'm having my maximum data points, as you can see, I have 506 data points from the data set that we have imported of load Boston. We have 506, so you can see this is very dense plotting of all the points here. But as my regression line, this is passing just straight from the point where we have a bulk of data points. Therefore it is telling that my data entry is, my data points are just giving a very good regression rate here. I want you to say one thing more. In the starting, we have just given some values for the learning rate, iterations, error thresholds. These values may differ. Your graph, your regression line may differ. If it is not coming to the maximum point, you just need to change the values and see where your regression line is giving the maximum prediction. And then you have to plot these points. This will make your project a good project that is giving you a maximum rate of iterations. Like in my testing data set also, we are getting the points. My linear regression line is passing from the points where I have the maximum data points, and in that training data set also my line is passing from the place where I have the maximum data points. See, this is very important, otherwise the predictions that we are going to make is also going to have some difficulties. Now what we are going to do is like we are going to see the error. The error visualization is definitely the most important thing that we have to always keep in mind, so that we should know that if the rate of error visualization is getting higher with the time that I proceed or lower. So we will just simply use the plot functions plt.plot and pass the parameters. We are going to use the numpy range function here, and up to the length of my error threshold, because that is the limit that I have allowed for the errors to occur, error values, and another parameter is going to be my error values here again. Alright, this is the point up to which I'm going to have my iterations. So good. What I'm going to do new here is just I'm going to provide the names to my axis. I'm going to label my y-axis as the error, and x-axis as my x label as my iterations, because it is the number of times it is going to move. Alright, let's see. As you can see, my value of the error is getting steeply down, and now it has gone to a concurrent parallel. It is neither increasing nor decreasing, it is just going to a certain rate. So as my error is going completely down, as therefore this is the point that I'm getting the maximum points covered with my regression line. So you have to ensure always that your error decreases with time as you go ahead with your project. If your error is not getting down, or if it is fluctuating, then you're not going to get a good prediction. So this is the way the error should be plotted. I mean, not exactly like this, but it always has to be going down. It cannot have a excess to it. Therefore, the error threshold is the value that we set to the very lower point, and therefore the error values are getting down. So this is the way. After getting through all the 4 last steps, now we have reached the final step where we'll be actually predicting the price of the project. That was the final output we were working so hard since long. Now what we have to do is we have to take a new variable called predict, in which I will just initialize it as m into x underscore test plus c. That is the equation of line, and such that I can use it ahead without calculating it for again and again. Next, what we are going to do is, like, we need to know what is the mean square error we have. We were talking about MSE. This is the MSE, that is the mean square error. We need to use this function from min-max scalar in order to understand mean square, in order to understand how close is our prediction going. For this, I'll pass the parameters, that is y test and predict. This will tell me what is the mean square. This is 0.02111 and so on. You can see the mean square value is so low. That means my prediction is going to be very near. Next, what we need to do is we need to use the NumPy vectorized operations so that we could visualize all our parameters in a tabular form and see how close is the value going. So I'll use a variable called p and just use the function of pandas data frame. This is nothing new that we are doing. We are just using this for once again because we need to visualize the list in a fantastic tabular form. So we are going to make use of the zip function again, which helps us see the table side by side, and we will now pass it the parameters that we need to see: x test, y test, and the predict. The next comes up is that we need to give the columns. What should be the name of our columns? So just name our columns x, target, y, because every value we were taking so far was from target, and the next will be my predict because this is the value that I am going to predict so far. And now we'll just print it. Let's see. And now you can see my target value and my predict value are really close to each other. This is 1819, 027, 0.27, and this is 0.35. This value is telling me that my value of prediction is really close to target. That means my project is giving a fantastic output. Now what we are going to do now is, like, we are going to just see this. Now what we are going to do is, like, we have to just visualize the output in a graphical form. For this, we are just going to use the same functions as we have been doing so far, that is plt.scatter. We'll just scatter our x test and y test values and give it a color, say it blue. And now we will plot our prediction line. plt.plot x test, comma, predict. Here we are not writing the equation of line because we have already defined our predict here, so we can just directly use it. And again we'll use the color red because it is going to be a line, and we have been using lines as red. So let's see. As you can see, this is the line again passing from the dense data plots, and hence my prediction is going really cool. So we have an evidence in the form of graphs, in the form of table, that our prediction is going really fantastic and is very close to the actual value. Next is what we are going to do is, there comes an important part. Now we will be just reshaping our data. Talking about reshaping of the data involves that we have to revert normalization. If you remember, when we began with normalization, we just reshaped the data from a range of -1 to 1 so that we could get all the data into a same frame and could get our values working. But now, as we have to give our final project output, therefore we need to get the prices in the actual form as we imported them from the data set. Load_Boston. So what we are going to do is, now we are going to get our values back into their normal form. So we'll just start with the predict. If we say using NumPy array, predict, and use reshape, sorry, it has to be sh, and -1 to 1. What we are doing here is like we are using the NumPy operation and taking the array of predict, all the values of predict, and putting them into reshape. What does my reshape function do is that it just reshapes the function from its previous values to its original values. And my -1, as soon as I put -1, my machine understands that it has to take the value that is given into the table at the runtime, and therefore 1 is the actual output that it will be displaying us. Next, what we are going to do is, we are going to reshape all the values, that is the predict, the x-test, and the y-test, because all of them are going to be really necessary for me to show my output. Therefore they all need to be in their real data format. So we will just get them all into the same form. X test, that is x_test. Again, we'll be using the reshape here, so I'll just simply use it, and test, y test. Right. We have to now scale them in the exact format as we have extracted them from the data set. So what we are going to do is, we just create few more variables called scaled, because we are scaling them, and we will just use the x_scalar and inverse_transform function that helps us to transform the variables from one form to another. Here we are getting them back into their original form. Comes y_test_scaled, and the same y scalar dot inverse transform. I'm sorry, I lost it. Yeah, and we'll just change it to y test. Next comes the predict_scaled. We will use the y scalar for it because all the values of predict are just coming from the same y value. So we are doing great so far. Now what we are going to do is, like, after scaling them all, we are just going to display them in the same format as we have used the NumPy array so far. Again, we will take a new variable called p and use the pandas data frame of function. Has to be a capital F. Okay. Data frame. Okay, and now we will again create a list, use the zip function. Just a second. Yeah, use the zip function and define all the parameters that we need to display x_test scaled, because we just changed our variables, and y test scaled and the predicted scaled. Next is we need to define the columns, that is we are going to give them the names. So the same step we are going to repeat just that we did earlier. Every value of y is from the target y, so it has to get a name target y. And now lastly the predict, that is also coming from y. So now what I'm going to do is, if I print them, they're going to be a large decimal values, hard to see, so I'll just round them to a decimal value of 2. This is also not new to us, we have done this earlier. And now we'll just simply print them and execute it. Predicted scaled, predicted, okay, I used the word ed here, and predicted scaled. So this is our final value for the prediction, and hereby we just give the final output of our project. That is, if we see we are giving the exact same values for the all total inputs that we are getting. The value of the target y and the predict y are exactly same for this. That means our project is giving a very good prediction. Now I would like to see all the values that we have been going so far. If you're wondering why it is taking just the 5 values, it is just picking up some random 5 values and printing them, because we were already working in the units of 5. And you see the data here. Every time we just plotted these data in the form so that we could get the maximum possible positive value for the prediction, and it is paying off in the end. Here also we had some slight variations, but when you see this frame, this is just exactly the same. This is a very good prediction rate that we are getting here. So this is our final estimation of price for the Load Boston project and data set we imported so far. Thank you.